Good morning, everybody. Pleasure to be here. I'm not quite sure how this is going to work here. I may decide to walk down in front. I can't quite see the screen or be able to use the pointer, but so there we go. I do have it on my laptop here, so. Yeah, I've got it right here. Yeah. Well, thank you very much. I am honored to be here with a lot of people that I know who are experts in a number of areas of ammonia. I am not an expert in anything. I know a little about a lot of things, and having worked with ammonia for about the last 30 years, in a wide range of issues, safety, regulations. I have a pretty broad perspective of ammonia, and I've been particularly interested in safety issues. Ammonia is used widely as a refrigerant. It has been for over 150 years. And anytime there is an accident involving ammonia, it doesn't matter if it's an agricultural fertilizer application or a large storage tank or a transportation incident, it reverberates through the whole industry. So I've always been interested in knowing as much as I possibly can about fatalities and serious injuries. Why did they happen? What went wrong? What can we learn from that? So a lot of the things I've done over the last couple of years is trying to share lessons learned with people in my industry and the entire ammonia industry, as well as first responders, so we don't have accidents again. One of the things I've learned in looking at all the accidents is almost every single one of them was preventable. And usually there's more than one thing that went wrong. It wasn't just a single event. And from my perspective, the people that are most at risk are the workers and the employees that are working right close to ammonia when there is a release. So what I thought I'd do today is go through just a little general background. I'm going to talk a little bit about hazards, risks, and threats of ammonia. And I'm going to talk quite a bit about doing risk assessments. And then I'm going to share a few things on accidents to give you a sense of the kinds of things that we need to be looking at to make sure we understand as much as we can. So to start off, you know, ammonia, I brought my little ammonia molecule with me today. I picked this up at a trade fair in Germany. I think it's actually a back rubber, but really looks like a little ammonia molecule. And so, you know, when we're talking about ammonia, we're talking about a fairly simple molecule, but a very abundant one. Ammonia is as natural as water. In the beginning, ammonia was the catalyst for life. I haven't been able to find that in the book of Genesis yet, but I think somewhere between heaven and earth, ammonia came in there somewhere. But it's a very critical chemical to life. There are a number of issues that are driving increased interest in ammonia. In the refrigeration industry, the issues of ozone depletion, climate change have led a lot of people to start looking at ammonia and more expanded use of ammonia because it has zero ozone depletion, it has zero global warming potential, and it's a great refrigerant. In addition, I think you'll be hearing about potential use of ammonia as a fuel here in the conference. So there are some interesting things going on that are all connected to environmental issues related to ammonia. What's in a name? You know, Shakespeare said, "A rose by any other name would smell as sweet." Well, ammonia by any other name would probably stink just as much. So it doesn't matter what you call it. But I found some rather interesting things. This is the hieroglyphic, Egyptian hieroglyphic for the god Ammon, which is where the name ammonia comes from. And over on the right are all of the various names that have been applied to ammonia over thousands of years. First one, sal ammoniac, salt of ammonia. That really came from the original uses of ammonia from camel dung in the oasis of Ammon, which is now over in Libya. Salt of Ammon is the English version. Spirit of hartshorn. Before we developed ammonia synthesis, a lot of the ammonia came from the bones of animal or the bloods of animal. Ammoniac, various spellings, NH3, anhydrous ammonia is what we typically all know it by. And I hope I got the Hebrew right there for ammonia. You'll have to tell me if it's right or not. Ammonia is a very abundant chemical. There are approximately 1 billion metric tons of ammonia that's generated in natural forms and by the human body. Natural production of, or artificial production, synthetic production of ammonia amounts to about 145 million metric tons a year. Our use of refrigeration is very small. It's a very small percentage of total ammonia. Interestingly, China is now by far the largest producer and user of ammonia, about 1/3 of the total world production. It wasn't all that long ago that the United States and Russia were the two largest producers. China has really jumped up. Back about 20 years ago, there were a lot of world-class ammonia synthesis plants built in China. Just for comparison, I put down at the bottom what estimated Israeli production is, 120,000 metric tons. It's 1/10 of 1% of the world production, but still a very important chemical to the country. Generally worldwide, about 80% of ammonia is used for various agricultural fertilizer products. About 18% is used in a range of industrial applications. Production of explosives, any process that needs nitrogen for an inert atmosphere usually uses ammonia. Water treatment plants. Like I said, less than 2% is probably used as a refrigerant. We really don't know, but it's a fairly small but important part. The history of ammonia is rather interesting. Back in the late 1800s, early 1900s, when the British did a lot of work on nutrients and discovered that nitrogen was a critical nutrient for plants, about the only source of nitrogen was saltpeter from Chile and bird guano from the islands off of Peru. So there was a huge trade of mining that bird guano, bringing it over to Europe, and that was the primary source of nitrogen back until right before World War I. Two people, a very brilliant Jewish chemist from the University of Karlsruhe by the name of Fritz Haber, and Karl Bosch, who was the president of BASF, the German chemical company, developed the Haber-Bosch synthesis process. This is Professor Haber's original model, or mock-up, laboratory scale synthesis process for combining nitrogen and hydrogen at high temperature and high pressure with a catalyst. Karl Bosch was a brilliant engineer. Karl Bosch was the one that developed the high pressure, the vacuum systems, the catalyst that allowed the synthesis of ammonia to be done very economically. And of course the Germans were very interested in having a source of ammonia because during World War I, their supply of the nitrogen from South America was blockaded. So it was kind of a critical national need. Fritz Haber is a rather interesting and almost a tragic character. There's some very good books written about him, and interestingly, both of them ended up winning the Nobel Prize for the contribution of ammonia to increasing world food production. If it had not been for their development of the synthesis process, we probably would have had a lot more food shortages in the world over the last couple generations. This guy you may recognize, very famous physicist by the name of Albert Einstein. What did he have to do with ammonia? Well, after the theory of relativity, he didn't have anything else to do, so he invented an ammonia absorption refrigerator. This basic patent, the co-inventor was Leo Szilard, who was the father of the hydrogen bomb. These units are still used. There are hundreds of thousands of these little ammonia units in recreational vehicles. They're run on propane, any source of energy. You can run them on solar. Very simple process. Back in about 1988, a couple of people I knew at the National Bureau of Standards in Washington were tasked by NASA to come up with a working fluid for the International Space Station. They looked at, I can't say, is it 860 or 680? I'm not sure what the number is. Did a complete screening of every chemical that could possibly be used as a working fluid on the International Space Station. This is the space station, and the little arrows that you can see there is where the working fluid works. What it does is cool the solar collectors and radiate heat back out through radiators to space. It's a very simple system. It's a heat pipe system. The only moving part is a pump. And guess what? They've had to replace that pump several times up there in outer space. But in spite of all of the issues with ammonia, with its hazards and toxicity and flammability, they concluded that ammonia was the best working fluid for its basic properties to do the job. And of course, in space, weight is a critical issue. So they were able to do the job with less ammonia than anything else. So they've had leaks up there in space. What do you think happens when you leak ammonia into outer space? I wonder if Tom's tried to model that in any of his dispersion models. What do you have in outer space? Absolute zero and a vacuum. So when ammonia comes out as a solid, little tiny white flakes. So when the astronauts are up there trying to change out the pump, they're in their suits, probably what we would call in the emergency response business a level A++++. Totally protected. They don't need to worry about anything. But they're getting all this little ammonia dust all over them. They go through the locker, the airlock. What happens to that ammonia? Boom, back to a vapor. They have some interesting challenges, and we had some of the people that worked on the ammonia system from NASA at our annual meeting a number of years ago, and they were scared to death of the ammonia that they were working with down at the Kennedy Space Center. The hydrogen and the hydrazine that they were working with in huge tanks didn't bother them a bit. Ammonia scared them to death. So there have been some interesting applications of ammonia. One of the things that's important for safety, for anybody working with safety or working with ammonia, is to understand the hazards, risks, and threats it poses as a material, as a chemical. Those hazards are related to its basic properties, its chemical, physical, thermodynamic properties. The risks are what happens if ammonia gets out of the bottle. The risk to life, risk to environment, and risk to your production, your product, your equipment, your processes. The threats that can cause those risks are kind of common things like fire, overpressure, any kind of release. And from the perspective of dealing with ammonia, how the release happens doesn't matter. Whether it's intentional, whether it's accidental, whether it's an act of God, whether it's a terrorist event, you're going to handle it the same way. You're going to deal with the release and not really worry about the cause. Some other things that are important to understand: the reactivity of ammonia with different materials, and of course, the kinds of things that can cause a release. So the keys to using ammonia safely is to understand the hazards, to manage the risks and control the threats. So the most important thing for anybody dealing with ammonia is to understand its basic physical characteristics, its properties. It's a colorless gas. It has a strong odor. Molecular weight is 17. It's lighter than air. Freezing temperature is about -78°C. Boiling temperature is -33. That's why we like it as a refrigerant. It boils at a very low temperature. And it has an ignition temperature. Ammonia will burn. It will ignite. Ammonia is one of the few gases that's lighter than air. So in its gaseous state, it's going to be buoyant. It's going to lift off. The chemical properties of ammonia that are important, heat of combustion, heat of formation. Latent heat is probably the most important thing for us in the refrigeration industry. It's the latent heat capability of ammonia that lets it be very efficient as a refrigerant because of the amount of heat that it can absorb. Ammonia has some toxicity issues. It's typically classified as a toxic inhalation hazard or toxic inhalation chemical. It is flammable. For years when I started in the industry, the old timers would say, ammonia doesn't burn, doesn't ignite. If there was an explosion, it must have been natural gas or something else. It couldn't possibly have been ammonia. Well, that never was true. The ignition temperature of ammonia is fairly high. So what makes ammonia a good refrigerant is its latent heat. Water is about the only molecule that has better latent heat, but water has this problem of freezing at 32 degrees or 0 degrees C, so it doesn't make a very good refrigerant if you want to have low temperatures. But other than water, ammonia is a great working fluid because of its latent heat. One of the characteristics of ammonia, if you release it under pressure, it will actually subcool due to the partial pressures, and you can get down to very low temperatures close to the freezing point. So when you're dealing with ammonia release, you can be dealing with cryogenic type of temperatures. Ammonia toxicity and flammability. I put up there some of the typical regulatory values for workplace exposure, for emergency response, PPE. Odor threshold for ammonia is pretty low, 5 parts per million or less, maybe up to 50 parts per million. People have a great deal of variation in their sensitivity to ammonia. I'm very sensitive to ammonia. I can smell it at very low levels. That's one of the things that gives it a good characteristic of warning before you get to dangerous levels. As soon as you smell it, then you know that it's there. Above 100 parts per million, ammonia can be very uncomfortable for most people. When you get to the 300 to 500 parts per million, it's almost unbearable. It won't kill you. You won't get seriously injured, but your eyes will tear, you'll cough, you'll have difficulty breathing. You want to get out of there. The fire and explosion hazard, the concentration that's flammable is typically in the 15 to 16% LFL up to 25% or more, depending on the humidity, the ignition source. One of the important things in refrigeration is when you mix ammonia with oil, it does tend to lower the flammable limit. The Ammonia Safety and Training Institute, which I was active in for a long time and served as chair, came up with this little chart, and we used to call it the rule of fives until they started changing the numbers. And the rule of fives was at 5 parts per million you can smell it. At 50, that's a workplace exposure, 8-hour kind of level you don't want people working in. 500 parts per million was a level where you need to be in some kind of personal protective equipment. 5,000 parts per million is getting to the point where it's potentially lethal depending on the length of exposure. So it's just kind of a shorthand to let people kind of benchmark what an exposure is. These are some of the regulatory values that we use in the EPS or US, and they're used generally around the world. Acute exposure guideline levels were set by the National Research Council of the US, ERPGs, is set by the American Industrial Hygiene Association. And they're generally, ERPG1 is something that you can tolerate that won't cause injury. 2 is a level below which you won't get any injuries, but it's got a fairly good degree of conservatism in it. ERPG 3 is where you start getting into the serious injury, life-threatening levels. One of the things to be cautious of, though, is the toxicity regulatory values tend to have a lot of safety factors and conservativeness built into them. If there's any toxicologists in the room, you probably will understand that, but they tend to take the most sensitive animal. They apply a safety factor because an animal's not a person, and then they apply another safety factor to deal with respiratory impaired people, elderly, children. So they're very conservative, and that gets to be important when you crank these numbers into doing modeling of how far a release will go, depending on the size of release. This guy, Paracelsus, is the one who said the dose makes the poison. And basically what he discovered was that almost any material can be a poison depending on the concentration and the length of exposure. And that's very true with ammonia. One of the things that it's kind of important to understand when you're doing risk assessments and doing emergency planning is the relationship between toxicity and distance. And normally when you see concentration versus distance curves, they're straight lines because they're on a log-log plot. But this rather dramatically shows you how quickly concentration falls off with distance. And these are some curves at different release rates using the Aloha dispersion model program. And what you see here is this is where fatalities happen. It's very high concentrations close to the release and depending on the length of exposure. So a 20,000 part per million exposure for a minute or two can be just as dangerous as a 5-minute exposure to a lower level of 5,000. So it's time versus concentration. This is where injuries happen. And we really don't have a good idea of what kind of concentrations can cause what injuries. We just don't have enough information about how people were exposed for how long and what their injuries were. But here's the tricky part. You see when you get down here to this line here is about 150 or so parts per million. And all these regulatory values we talked about are below that. So when you get out here to long distances, this curve just kind of keeps going and going and going and going and going and going and going. So you can get low concentrations at long distances. But they're concentrations that people can smell. And they might panic, they might get worried. But it could be 50 or 25 or 100 or 150 parts per million. So this is where we have challenges with modeling, with releases, with the toxicity values. And you get out to very long distances and we really don't even have data to validate a lot of those concentrations. What we've learned from a lot of accidents is almost all the fatalities happen within a few hundred meters of the release. Doesn't matter how big the release was, but they're kind of in this inner circle. Injuries kind of tend to be out a little bit further, but the people that can smell it, be affected by it, be concerned, might call the fire department saying we don't know what to do. That can be a long distance and a lot of people, depending on which way the wind's blowing. The flammability issue for ammonia, this is just sort of a comparison of how ammonia stacks up to traditional hydrocarbons that have a much lower LFL. One of the things about ammonia is it takes a very high ignition energy source to ignite it. And when it does burn, it's a deflagration, not a detonation. So it's almost like a flash fire. If you see an ammonia ignition, it's a whoosh. It's not a bang. It's a subsonic pressure wave. It's a low, slow rise pressure wave. It's enough to take out a wall or a window if you can't vent the pressure, but it's not a detonation or a bang. Every time I see a report of an ammonia explosion, the first thing that goes up is, okay, was it really ammonia, and was it really an explosion or a detonation? The risks from ammonia that you want to try to manage have to do with risks to life, the environment, and your product, your equipment, your processes. The life risks are mostly respiratory, exposure to moist parts of the body, skin and eyes in particular, and also a number of things that ammonia can trigger: nausea, cardiac sensitization, heat stress, shock. Respiratory inhalation of ammonia is the largest health safety risk of ammonia. If you breathe ammonia in, you breathe it into your lungs, the ammonia reacts with the water in your lungs, turns to aqua ammonia, which has a very high pH, and it basically destroys the lung tissue in your lungs. So you're not able to breathe. You're not able to get air into your body, into your lungs. So it's inhalation exposure is the #1 issue in terms of public health risk. If you get ammonia on your skin, if it's minus 33 degrees, it's cold, you're going to get a cryogenic burn. But ammonia is a strong alkali. So when that ammonia reacts with liquid in the water or moisture in your skin, it again turns to aqua ammonia, and you're getting a very high pH. It can be 10.5, 11.6. So you get an alkali burn. Alkali burns are a lot different than acid burns. Eyes are probably the most sensitive organ to ammonia. Your eyeball has a lot of liquid in it. So we always tell people never wear contacts when you're working with ammonia, because if you get that ammonia back behind your eye, it's very difficult. The best thing to do is copious amounts of water to flush the ammonia out. So working around ammonia, good pair of vented chemical safety goggles is very good eye protection. Then a number of things: nausea, cardiac, these are kind of secondary effects to exposure. Environmental risks, ammonia is part of the natural nitrogen cycle. So it's constantly circulating from the air to the ground, changing form from ammonia to ammonium, various nitrates. But if you spill ammonia and it gets into water, again, the same thing happens. Ammonia is very hygroscopic, so when it reacts with water, it produces aqua ammonia, very high pH. High pH is very toxic to fish, along with ammonium ion. So you have to be very careful about spilling ammonia into water. In our industry, having an ammonia release inside a cold store or a food plant, it will contaminate the product, particularly if it's a moist product, fish or produce. So you can lose a lot of product. Your production line can be down for days and hours. You can have employees off work. So anybody using ammonia as a refrigerant has to be concerned about that. You're going to hear a number of presentations about dispersion of ammonia in its different states, so I'm just going to mention this is another one of the curves that shows concentration versus distance and how ammonia plume will react. I want to talk a little bit about risks. There is no such thing as zero risk. Anybody that tells you that is the case isn't telling you the truth. And there's a couple things that happen with people dealing with ammonia. Black swans and black elephants, if you've read anything about that. Black swan is something that's happened that you don't know about. Somebody else had an accident. You're not aware of it, so you don't factor it into your planning. It's kind of one of those unknown knowns. It's known that something's happened, you just don't know about it, so you don't factor it into your planning or your risk assessment. A black elephant is something you know about, but you just don't want to deal with it. You want to ignore it. Costs too much money. It's too much of a hassle. It's too low a probability. We don't think it'll ever happen. That's what tends to get people in trouble more than black swans. And I kind of came up with another term, a black unicorn. That's kind of a fictitious animal that you just make up. You know, we think a bunch of stuff could happen, but we don't know it ever happened. We haven't experienced it. We just think it could. This is one of my favorite cartoons. Was a U.S. cartoon called Calvin and Hobbes. He was a little boy who had a stuffed tiger as a pet, and the tiger talked. So this was one cartoon where he was doing worst case analysis. So the cartoon is basically there's a jet airliner that loses power and it starts crashing to Earth. Then there's a train going 80 miles an hour and it derails and starts to head off. And then at the same time there's an earthquake that started, and here's this poor guy in a house that's getting ready to light his stove and he's got a gas leak. And the airplane, the train, and the earthquake and the gas explosion are all about to happen at the same time. That's a black unicorn. And then down in the corner, Hobbes says, "Can we play something else?" So you really need to be careful in doing risk assessments to do things that are credible and defensible. A typical risk evaluation, when we're dealing with ammonia in large amounts, we're dealing with a potentially low probability but potentially high consequence event. Those are tough to deal with because we really don't have enough experience to know what the probability is. It maybe never happened, but is the probability zero? Remember what I said about there's no such thing as zero risk. It's not going to be zero, but you don't know what it is and how likely it is. The consequences, you know from the hazards and the risks and the threats we talked about. So when you start dealing with low probability, high consequence events and trying to predict or do a risk assessment, that's where things really get dicey. This is a typical probability curve, what most people would consider unacceptable is a fairly high probability of happening. Most industrial accidents kind of fall in this range. Natural disasters are up here. 1 in a million is the standard criteria for regulating a chemical that could cause cancer. Getting struck by lightning is higher than getting cancer. A good friend of mine in Sweden did some analysis of fatalities, and he thought the number for risk on ammonia fatalities was about 2 in a billion. As good as numbers I've got, it's fairly low, and the probability of a fatality from an ammonia release is fairly low. And normally, those kind of probabilities don't justify taking extraordinary or extreme regulatory measures. What I've learned in all the instances I've looked at, the victims are almost always very close to the release. You don't find victims 5 miles, 10 miles, 20 miles downwind. Most of the fatalities happen to workers and employees because they're the ones that are right there when the pipe breaks or the valve opens up. And what I have found time and time again in all of these incidents, they weren't wearing any PPE. No goggles, no gloves, no face shields, nothing. No face mask, no APR. So doing high-risk tasks without PPE can be very dangerous. The threats from ammonia come from fires. Overpressure causes a lot of ammonia releases. Safety relief valves pop, pipes rupture. Releases, reactivity. Ammonia is very reactive with some metals, copper in particular. It's also reactive with water. You'll hear a lot more about types of releases, but typically an ammonia jet coming out will be an aerosol. There will be suspended liquid droplets suspended in vapor. That can be heavier in air, it will slump down, you get a dense gas cloud, but eventually as it warms up, and remember the latent heat issue, you got a liquid droplet, you've got to add close to 600 BTUs per pound to evaporate that droplet and turn it into a vapor. But eventually it will turn to a vapor and it will become buoyant. Now a little bit about accidents. 30, 40 years ago, there was very little regulation of the chemical industry. But it took a number of major accidents. Flixborough in England was a hexane explosion. Seveso in Italy was dioxin. We had Love Canal in the US, Times Beach was dioxin. Bhopal, methyl isocyanate, killed over 3,000 people. And just recently in the US, we had West Texas. That produced around the world and in most countries a host of regulations dealing with occupational safety, environmental, transportation. Most recent ones are chemical safety and risk management, and then homeland security dealing with terrorism threats. But they also generated a lot of industry codes and standards that apply to the equipment. Here's a couple of major incidents in the US. These are some of the largest ones that I know of. Terra Nitrogen in Sioux City was a very large refrigerated atmospheric ammonia tank. December 1994. These releases always seem to happen in the winter when it's cold and it's overcast, which is about the worst kind of condition you could have for an ammonia release. But it was a ammonium nitrate process reactor that blew up. It threw shrapnel through this tank. Some of the pieces were the size of a television set. It went all the way through the insulation, the jacket on the outside, the insulation, the steel, through about 40 or 50 feet of liquid ammonia into the steel on the other side. That's how much force was behind it. When that tank got punctured, it was like a shotgun shell had hit it, and the ammonia started leaking out into a dike. That tank was connected to another tank with a crossover pipe, and as the liquid level went down in this tank, the level in the other tank proceeded to fill it. So they dumped almost 6,000 tons. It's about the largest ammonia release I've heard of from that kind of a refrigerated storage tank. In addition, shrapnel rolled a couple of 90-ton pressure vessels off of their saddles and punctured the end. But what happened here is when the ammonia released, the liquid subcooled, and somewhere right about in here you can see a frost line. The liquid stayed in that tank for a week because there was no heat energy to boil it off and evaporate it. This one is a transportation incident in Minot, North Dakota. Again, January, North Dakota. Very cold. It was a railroad car derailment. 5 tank cars ruptured, and they ruptured catastrophically from impact. So when you see these cars lined up, they kind of stacked up like cordwood across the rail, and one car ran into another. And when those couplers hit the cars, steel gets very brittle at fairly high temperatures, 25, 30 degrees Fahrenheit. So the steel tanks ruptured. This is one of the tank cars that flew about 1/4 of a mile. The end came off and it shot like a rocket. But in all of that release, 150,000 gallons, one person died. That person was in his house. It was a foggy day. The ammonia cloud made visibility very poor. He tried to get in a truck and get out. He ran into a building and got out of the truck, and they found him behind the truck. If he had stayed in his house, he probably would still be alive today. This one was caused by faulty track on the railroad. One of the things I'd like to convey is why you shouldn't believe everything you read on the internet. You can find all kinds of stuff. I Google ammonia every day, and there isn't a day goes by that there isn't some kind of an ammonia release reported on Google. But you need to be very careful about these things because very often there's incomplete information or simply wrong information. Here's a classic. I told you about the West Texas ammonium explosion. This was a story right after the event in National Geographic magazine. Headline, explosion highlights danger of anhydrous ammonia. When the accident happened, the only thing they knew is this was a small agricultural co-op facility. They had ammonia, they had reported. Nobody knew they had ammonium nitrate. And down here at the bottom it says, people thought the explosion sounded like a nuclear explosion. Huh? When I saw the first videos of cell phone videos and I heard that bang, I knew immediately it couldn't have been ammonia. It had to have been a detonation. It had to be a very high energy explosive. And sure enough, this is the facility before the event. This is the building that sort of got vaporized. These are a couple of ammonia tanks right here. Here's the same image. Here's about a 90-foot crater where the building used to be. Here's the ammonia tanks. They were still there. They still had ammonia in them. You can see a little bit of white vapor kind of coming out of one end of one of the tanks. So very often early press reports, they're incomplete. They don't have a lot of information. So be very cautious of things you pick up off the internet. And if it doesn't sound right, kind of dig into it and see if you can find an explanation. Okay, the last thing I'll cover real quick is just some lessons learned from ammonia releases. Couple of general points. Ammonia releases are common. Unfortunately, they happen all the time, and because people can smell it, they get picked up in the press. But ammonia accidents that cause significant consequences, I'm talking about multiple fatalities, very serious injuries, significant off-site consequences, are actually fairly rare. If there's one that happens in a year, it's probably unusual. There are also common things that happen in all of these accidents and releases, time and time again. And nearly all of them, as I said, are preventable. This is a traditional safety triangle, and what it says is you have a lot of common small incidents, but only a rare serious one. But if you pay attention to these small incidents, the near misses, and try to address the safety issues that they're illustrating, then there's a good chance that you'll never get up to this top here. And there's some very good work that was done back in the 30s on the safety triangle of accidents. I spent a lot of time with the U.S. Chemical Safety Board. We looked at accident data in the U.S. and around the world. There's some very good data that comes out of the European Union, reported under the Seveso directive, called the Mars database. There's a very good French database called AREA, the BARPI. And then the Health and Safety Executive in the UK also collects data. This is from some of the OSHA data, U.S. Labor Department workplace injuries. And what it kind of shows you is the most common cause is equipment failure. And OSHA didn't identify human error as a major cause, but they're kind of a labor organization and they don't like to put blame on workers. You'll see something different in the EPA risk management data. These are the top 5 chemicals in the U.S. That are regulated under the Environmental Protection Agency's risk management program. Ammonia is by far the most frequent chemical, most frequent number of facilities. Chlorine's number 2. Those are the 2 really hazardous materials we deal with. When I looked at the RMP database over about a 20-year period, it's about 8,000 facilities using ammonia, about 2,000 incidents, a very robust set of data, and there's a lot of information reported by companies on what happened, how much was released, what time did it happen, what were the consequences. Unfortunately for my industry, 60% of those come out of refrigeration. We have a lot of incidents. So ammonia is the #1 covered chemical regulated in the US, and it's the #1 reported accident history. And most of the accidents happen in refrigeration, relatively few in the process industry and the fertilizer industry. This is kind of the most important thing that comes out of it. The #1 source of releases is valves. #2 is piping. Piping connects a lot of valves in complicated process systems, and that kind of makes a lot of sense. The other category that's big is a hodgepodge, but it's a lot of overpressure releases from safety relief valves. You shouldn't have safety relief valves going off for overpressure reasons unless something's happened in the system that shouldn't have happened. Something else went wrong. Some safety control failed. So the safety relief valve is your last line of defense. This is the other interesting thing. Mechanical integrity, equipment failure is #1, just like OSHA says. But human error is #2. It could be training. It could be operating procedures. It could be lack of wearing safety gear. There's a lot of human factors that can go into it. It's not necessarily the worker. Maybe the job wasn't designed right. Maybe the operating procedures weren't done right. So to really understand what's driving a lot of these accidents, you need to burrow down a lot deeper. Here's kind of the takeaway. For ammonia, for me, the #1 issue is worker injuries. It's people working around ammonia when there's a release, and they are by far the most affected. Public, nah. First responders, nah. And here's the other one, fatalities. We have about 1 or 2 fatalities a year in the US from ammonia accidents to workers. Public, doesn't really get off site much. First responders, very rare. Finally, a couple of comparisons. Ammonia generally has a very good safety record compared to a lot of other chemicals. This is the number of incidents per facility. So ammonia and, what is that? I can't see that. Propane? Butane, okay. That's a flammable. But you get up here to phosgene and HF, there's about 1 per facility release. And here's the injury fatality data. Again, fairly low, very good on ammonia in terms of number of injuries per incident and number of fatalities per incident. So, bottom line, looking at ammonia from a safety accident point of view, ammonia is one of the highest volume chemicals in the world, usually in the top 5. We've used it safely for 150 years. Large catastrophic releases are rare, and those that happened were preventable if people had followed proper design guidance and good practice procedure. Greatest risk of harm is to employees and workers. Happen to be in very high concentrations when the release happens. A couple of other things from looking at the history. Large volume storage and handling at low pressure is safer and less risky than handling pressurized ammonia. And you'll hear more about that in some of the dispersion discussions about what happens with a flashing pressurized liquid release. Assessments of risk and consequences have to be credible. They need to be based on realistic assumptions and without overly conservative criteria. You can worry yourself to death over scenarios that really aren't at all realistic. Ammonia is a chemical that deserves respect, but not fear. If you understand ammonia, you understand its properties, you understand how it reacts in different situations, then you can respect it and handle it safely. So with that, I will conclude, and thank you very much for the opportunity to speak.